gotten a little dusty between the last class and this class. So we talked about products and moments of areas. First area moment, second area moment, which again, you learned in statics and maybe somewhere else in your education. And conveniently in the back of your book, you are given, I know this is really hard to read, but it's in the back of your book. This is a page right from the back of your book. So you have the moment of inertias, how to calculate the area for simple regular shapes, as well as the location of where that center of area may be. And then what we did was, we were looking at trying to take this pressure distribution that we've identified, P is equal to minus gamma Z. We're trying to take that pressure distribution and now convert it into a force. So we looked at taking some area, and that would be the yellow area here, when you're looking at the edge of the area. But if you look down on the area, oops, where'd it go? No, I don't have it in this picture there. So what we did was look at the pressure distribution from the top to the bottom of the area. That pressure distribution acts everywhere normal to the surface, and what we wanted to do is convert that pressure distribution into a force, which is also normal to the surface, because all the pressures are. So that was our charge last time, and what we did was we recognized that we could divide the surface into differential strips of size dA, and since they're horizontal strips, the pressure on that horizontal surface is a constant. And so the force dF on that differential strip dA is just the pressure times the area, PdA. And we know that the pressure is just going to be the specific weight of the fluid times the depth of submergence, H, wherever that little area is. So again, we took some area that looks like this, and we divided it into horizontal strips, dA, and this is somewhere below a free surface, so we know the depth of submergence to that little strip. And so again, we can calculate the differential force on each one. We also said that, as I showed in the previous slide, this surface doesn't have to be horizontal or vertical. It could be in any inclination angle. And so what we identified was the inclination angle off of the horizontal is going to be theta. And so if we have the surface, for example, here, and it's inclined theta off of the surface, along this axis, which goes from the free surface along the inclination, that's going to be the y-axis, we can convert any vertical dimension, h, into a dimension along the y-axis, which is, again, an axis that goes right through this inclined surface. In this case, the vertical dimension would be the inclined dimension times the sine theta. And therefore, in the equation up above, where we had a vertical dimension, dF is equal to gamma h dA, we can substitute y sine theta in for h. And then what we did was recognize that if we integrated all the little dF forces over the surface, that gives us the total force. And so, again, the integral over the entire surface area of all the little dF forces is equal to the total resultant force of the fluid on the object, on the side of the gate, on the side of the object that we're looking at. So more often than not, you only have fluid on one side of the submerged plane surface. But you could certainly have a problem where you have the fluid on both sides. And so now, from the previous slide, we substitute in what we know for dF, gamma y sine theta dA. And we recognize that the specific weight over the dimension of this object that we're looking at, as well as the inclination angle, since it's a plane surface, can come out of the integrand. And when we, you're always in the way. So when we do that integration, what we see is that the integral of y dA, which is what we were looking at last time when we talked about moments of areas, is equal to the distance from the free surface along the inclined axis to the center of area. We call that distance y bar, times the area itself. So the integral of y dA is equal to y bar A. That's what we derived last time. And again, we can put y bar sine theta in terms of h bar. So again, we can look at a dimension along the inclined axis. We can look dimensions along the vertical axis. But when we look at this closely, whether you're talking about y bar or h bar, an inclined dimension or a vertical dimension, when we look at what that statement is saying, gamma y bar sine theta or gamma h bar is the pressure at the center of area. And when we're multiplying that pressure at the center of area times the total area, you're getting the resultant force. So very simplistically, with all of that calculus we just did, what we found was, last time we ended with this, that the resultant force of the fluid pressure distribution on one side of this plane object is simply the pressure at the center of the area times the area itself. So if you have a circle, what's your area? Pi over 4d squared. Where's the center of area? Right at the center of the circle. If you have a triangle, if you have a rectangle, typically we know where the center of areas are for these regular shapes. And so this is actually the equation you're going to be using, and there's really not a lot of mystery to it anymore. So again, if you're a golfer, PGA. So the next thing, that's just regurgitating it. The next thing we're after is, where does that force act? And again, because you have a pressure distribution that is increasing linearly over the object, and you may not have a very simple regularly shaped object like a circle or a rectangle, the force is not going to act at the center of area because you have this pressure distribution that has more pressure at the bottom, deeper into the fluid, on the lower part of the object than above. But again, what we can do is employ a differential approach in order to find what we call the center of pressure, CP. So in the previous slide, CP is the center of pressure. And so if you look at this diagram, here is our area. And again, along the y-axis, where I'm drawing the red now, that's the edge. We're looking at the edge of the surface. When we look down on the surface, we see this almost figure-8 sized surface. And when we look down on the surface, we can see that there is a center of area somewhere. And what we're trying to do is find out where the center of pressure is. The magnitude of the force is related to the pressure at center of area. F is equal to PGA. But the force will not necessarily act at the center of area. You have to understand that. So, again, the inclined axis is the y-axis, and it goes from the free surface right through the inclined axis. And to the free surface, y bar is the distance along the y-axis from the free surface down to the center of area on the object. YCP is going to be the distance from the free surface down to center of pressure. We want to know where that is. We need to locate it. And again, for any inclined dimension y, we can convert that into a vertical dimension. So y bar sine theta is h bar. YCP sine theta is HCP. Those 1 6 together. So, as we talked about before, we're going to have this surface, same definition sketch. So the yellow line you see is looking at the edge of this plane surface. And from the top to the bottom, again, if you look down onto the surface, it looks like this irregularly shaped object. On that irregularly shaped object, we have a center of area. And we know that the magnitude of the force is going to be the pressure at the center of area times the area. So as we did before, in order to calculate the magnitude of the force, now what we want to do is figure out where the force acts. And we're going to do the same thing we did before. We're going to divide the object, the surface, into differential size strips dA. And on each dA, there's a force dF, just like before. Only now what we're going to do is say that each of these forces, dF, has a moment arm to the free surface. And what I want to do is calculate the moment of dF about the free surface. Why? Because ultimately there is some resultant force, F. That's the magnitude of the resultant force. And its moment arm to the free surface times the total force has to be equal to the integral of all the little moments, Fy, dFy, over the entire surface. So just like we did with force, we're looking at the moment about the free surface due to the entire force and equating that to the integration of all the distributed forces across the surface. So again, we have this horizontal strip on dA, and what we're hoping to find from this analysis is the distance from the free surface down to the center of pressure. So again, if we are looking down on the object, the x-axis is riding along the surface of the water into and out of the screen, or into and out of your paper. But now we're looking down on the object so we can see this x-plane. And so yCp, again, is the distance from the free surface down to the center of pressure. Y bar is the distance from the free surface down to the center of area. And likewise, right now I was just focusing on taking moments about the x-axis, the free surface. But we could take moments about any axis, for example, the y-axis, and what that would give us is exactly where this point acts, from the y-axis and from the x-axis. And so we're going to have to do both. So again, we're going to take moments about the free surface. The moment of the total resultant force, F, about the x-axis, is F times yCp. yCp is what we're trying to find. Capital F, the resultant force on this submerged surface, acts at yCp. Fycp, the moment of the resultant force about the free surface, is equal to all the distributed dF forces. Each dF force acts on each strip dA. And each dA has a distance y to the x-axis, which again is the free surface. So in a mathematical form, what we're saying is that, again, the resultant force, Fycp, is equal to the integration over the area of all the little moments due to each dF on each dA times their moment arm y. So as you take different horizontal strips dA through the area, it's going to have a different distance to the y-axis. So y is a variable in that case. And again, from before, when we looked at just calculating the force, dF is gamma y sine theta dA, where gamma y sine theta is the pressure acting on that little surface dA. So dF is pdA, all what we said before. So now what we have to do is take this equation and substitute in for the left-hand side. We know that the resultant force F is Professional Golfers Association, PGA. It's got a moment arm yCp to the free surface. And you can see that we brought gamma and sine theta out of the previous integrand because they're constants. And again, the integral over the area of y squared dA, you should now recognize as an old friend. So the first thing you recognize is further, we can expand PG. PG is the pressure acting at the center of area. And PG, again, as we identified before, is the specific weight of the fluid. Y sine theta is h bar, the depth of submergence of the center of area. And then to get the force, we still have the area. And then the right-hand side is basically remains unchanged. But what you can see is gamma sine theta on both sides of this equation are going to cancel. And what we want to do is just solve this equation for yCp, the distance to the center of pressure from the free surface. And so when we do that, what we recognize when we rearrange the equation is, I'm just going to go back one. So we cancel gamma sine theta, and we brought y bar and a to the other side of the equation. So you have 1 over y bar a. So there's the equation. YCP is 1 over y bar a, integral over the area of y squared dA. And again, that's an old friend. We developed this last time. This is the moment of inertia of that area about the x-axis. In your book, one of the first slides of today, in the book they give you the moment of area about the centroid. Those two are not the same thing. But last time I went over the parallel axis theorem. We know how to get from one to the other. And that's the substitution we're going to have to put. So, again, that first equation just says that the distance to the center of pressure, where the resultant force acts, is equal to the moment of inertia about the x-axis divided by y bar a. Y bar, again, is the distance from the free surface down to the center of area. A is just the area of this plane surface. So, you said that. And I've said this before, I haven't said it repeatedly. If I'm going too fast, either on the chat or in here, just ask me to repeat something or go back to something. It doesn't bother me. I get paid by the hour just like you do. Okay? So, this is the equation we had. That the distance to the center of pressure is equal to the moment of inertia about the x-axis divided by y bar a. We introduced the parallel axis theorem last time. And all that said, in what we want to relate to, we want to move this from the moment of inertia about the x-axis to the moment of inertia about the centroid. The equation we developed last time was that the moment of inertia about any arbitrary x-axis is equal to the moment of inertia about the centroid plus the distance from that arbitrary x-axis to the centroid. And on our definition sketch, remember, the x-axis rode at the free surface. That's where the y-axis started. So the distance from this arbitrary x-axis, which in this derivation happens to be the free surface, to the centroid is y bar. That's how we've always been defining it. Okay? And so now we take that definition of Ix and substitute it into our equation for YCP. And so you can see that instead of Ix in the last equation you're seeing right now, YCP is equal to the moment of inertia over y bar plus y bar squared a divided by y bar a. And then we separate the variables, so you have moment of inertia over y bar a. And then the second term, y bar squared a divided by y bar a, is just y bar. So let me ask you some very challenging questions. And this is a competition now. It's between those on chat in Zoom and those in the class. I'll be the judge. Is IG ever negative? Yes or no? Okay, anybody answer this? Is it ever negative? No, it's never negative. It's never negative. Where is the y-axis starting? At the free surface. And so all of our y values are always positive, right? By design. Is y bar ever negative? No. Is the area ever negative? Come on, this is the quiz. Am I getting any chat responses?
No, one now.
One. Is the area, I see it now. Okay, so it's 1-to-1 now. I saw someone actually shaking their head here. The area is never negative. So that first term, IG over y bar A, is never negative. It's a positive number. Let's go to the second term. Is y bar ever negative? Have I already asked that question? It's a positive. So what does this equation say? YCP is equal to IG over y bar A plus y bar. This is a positive number. IG over y bar A is a positive number. This says that the center of pressure is always at or below the center of area. That's what it says. And that's because of the pressure distribution. There are larger pressures typically below the center of area than above. Again, my CP always acts at or below the center of area. How would that first term go to 0? What would make it go to 0? There's 3 ways you can go to 0, right? Sure. Let's
The
hear
area
it.
gets huge.
What?
If the area gets really, really big.
Area gets huge. That's one way. I agree. Any other answers? TAs, shout out if somebody checks it in.
We are if the area is huge.
The area gets larger. What else could make it go to 0? Come on, there's 2 other terms there. IG goes to 0.
Y is huge.
Y is huge.
Or Y what?
Is huge.
Increases. So think about designing something. You're designing a gate that's going to sit under the water. Is that gate going to change size over time? Do you expect it to be changing? No. Therefore, its area and its moment of inertia are not going to change with time. However, what could change? Could you put this gate under deeper and deeper submergence? Sure. So the take-home message is, as the depth of submergence or the pressures get larger and larger, given one constant surface, say it's a rectangular gate, as it goes deeper and deeper in submergence, YCP slowly moves up to Y bar. For very deep depths of submergence, YCP and Y bar are at the same location. But when you start very close to the water surface, they're going to be about as far apart as they can be. You get that? I know. You're reluctant to say you get that because you want more homework, so I promise I'll give you more homework. Okay, so again, moment of inertia is about the centroid of the button. So we took moments about the x-axis. We want to do the same thing for the y-axis because again, right now we know along the y-axis or along the vertical axis, now we know where the center of pressure is, but we don't know where it is laterally on the object. And that's why we have to take moments about the y-axis to figure out where the force is acting laterally. And so we're going to do the exact same thing we did before, only instead of taking moments about the x-axis, we're going to take moments about the y-axis. And if we're looking, again, at an object, let's say this is our object. And let's say it's vertical. So it's this odd triangular gate and it's vertical. And so let's say that the center of area G is here. All right? The center of pressure might be over here. Okay? And so what we're trying to do is, before we took moments about the x-axis, now what we're going to do is take moments about the y-axis. And the y-axis, as I've been showing you, goes through the inclination angle of the surface. It could be anywhere. It doesn't have to, like the x-axis, it doesn't have to be on the object. Could you draw an x-axis here? Or, sorry, a y-axis here? Absolutely. Okay, so right now, I'm just going to say that the y-axis is kind of arbitrary. But what we did before was, with taking moments about the free surface, we related everything to the center of area. And at the end of the day, when we take moments about the y-axis, we do the same thing. So, just as we did before, we say that the total force, capital F, with its moment arm, so again, F is acting here, and its moment arm is XCP. It's the distance from the surface over to the y-axis, wherever that y-axis is. And we're saying that the moment of the total force about that y-axis is equal to the distributed moments. Now what we're doing is cutting up the area into little vertical strips, or strips that are parallel to the y-axis. And so each one has a depth of submergence, which is varying, but the dF is always going to be equal to PGA. The pressure on each of those little dFs is always going to be PGA. And since these are differential areas, you can kind of approximate them as rectangles. And so the center of area is just midway down that little rectangular dA area. So this isn't challenging. And we'll do the same substitutions we did before for the total force and the differential forces. And then we'll, when in doubt, cancel out the gamma and sine theta on both sides of the equation. And what we're left with is the distance from the resultant force to the y-axis, xcp, is equal to ixy over y bar a. And remember last class, I introduced this to you because it's rare in statics when you use what's called the product of inertia, ixy. It's not in your books. So we'll need to talk about that. So again, ixy is the product of inertia, and it's the moment of the area about both axes. So you see this xy term in there. However, for ycp, we had an equation like this. We moved it from an arbitrary axis to something through the center of area. I'll get back to this one. One thing you can recognize is ixy, the product of inertia, is 0 about an axis of symmetry. So again, we typically have symmetrical objects. Let's say we're going to put in a square gate. So here's the center of area for the gate. And we can calculate where ycp is for this gate. But now we're trying to figure out where it acts laterally on this gate. If you look at this rectangle, is there a y-axis that we can draw that would be an axis of symmetry? If the y-axis goes through the center of area of this rectangle, that's an axis of symmetry. And what this equation says is that the product of inertia is 0 for an axis of symmetry, which when you put it up into this equation, xcp would be equal to 0 when your y-axis is an axis of symmetry. What that would say is if xcp is 0, that the center of pressure acts directly below the center of area along the y-axis. Again, that y-axis can be inclined or vertical, right? So, in most engineering applications, we typically have nice symmetric objects. And in here, I'll probably just be giving you squares and rectangles. When you leave here, could you make a gate that looks like this? Absolutely. You're going to pay through the nose for it, but now you also have to find the product of inertia for it. And how you can do that is the same way you find the moment of inertia for it. Divide it up into smaller regular objects, and then build your moment of inertia that way. I don't know if you still do that in statics, but if there's a way of doing that. And in a few more lectures, we'll talk about forces on composite surfaces, irregular shapes, and I'll show you how we do that. So, I want to go back a few slides because I said this slide was out of order. So, the location of the resultant force along the y-axis. I left you with this equation, but if we just bring y bar to the other side, ycp minus y bar is equal to ig over y bar a. Again, that right-hand side is always greater than or equal to 0. And what that says is that ycp minus y bar must be greater than or equal to 0. So again, the center of pressure is always at or below the center of area. That's what that says. Okay. Great. So, example. In the book, sometimes things can be abstract, so I tried to pull down some pictures for you. So this is a gate, and this gate is going into an opening here, and what you see is a dam over here. And so the gate's going to be put in place to be able to throttle or control the flow. So typically, if you're doing, for example, flood control, the gate's open, and whatever comes in the reservoir goes out. But if you notice a big rainfall event's happening and you want to control the flood, you shut the gate, and downstream you have no water going through the dam now, and all this flood water going in and filling up the storage. So you have a lot of water on one side of the gate and none on the other. Now, obviously, they don't do that. They will let some water go by because evidently there are aquatic organisms in these streams, so they don't want to dry up the stream completely. So that's the gate. And this is you counting to 4. And now you can see where the gates are in a fixture. So the piece up above is the bulkhead. And 1 and 2 are bulkhead gates, 1 and 2. And basically, again, they just slide up and down. They could be oriented on an inclination. They can have any orientation. But when you hear this bulkhead gate, it's just some type of a structure that looks like this. So this is now the conceptual drawing of that same last figure. In this case, here's the bulkhead, big concrete structure, and there's the gate. We've got a free surface on one side, so this could be our design condition when the gate's closed. So that means you have water on one side and no water on the other side. And what you may be trying to do is size the structure that's going to hold this gate in place and make sure it doesn't blow out. There are some structures we designed, for example, flashboards on top of dams, that the water can go over the top of them, but if it gets too high, the force just keeps increasing and then they just collapse. And what that does is prevent flooding upstream of that system by allowing the flashboards to collapse. So we need to calculate the force and we need to know where the force acts in order to size the structural competence of these considerations. So what you see is the top of the gate. So the gate is right here. That's the gate. You're looking at the edge of it, and the top is 4 meters underwater. The bottom, well, I'll get to that. If you look at the gate face on, you see it's 1 meter into and out of the border, into and out of your paper. That's the gate depth. And then the gate height is the 2 meters. So if the top of the bulkhead is 4 meters below the surface, the bottom of the bulkhead is 4 meters plus 2 meters, or 6 meters below the surface. If anybody has a calculator, if that's the center of area, how far is the center of area from the free surface? 4 meters to the top, and if the height is 2 meters, then G must be 1 meter down from the top. That will be 5 meters, right? And again, if we know where G is, and we know the fluid, we know the pressure at the center of area, and therefore we know the force. So the first thing you always want to do in these problems is recognize the information you're given. And I haven't, so the problem is here, find the force of the water on the gate and where the force acts. That's what we're after. And this is a vertical gate, and in a vertical gate, theta is 90 degrees. Sine of theta is sine of 90, which is 1. How convenient. And here we walk, and then we run in fear. So we'll get to much more difficult problems. So the gate dimensions are 2 meters high by 1 meter wide. That gives us an area of 2 meters squared. Theta is 90 degrees, and therefore the sine of theta is 1, which means that the z-axis, which we always call vertical, the y-axis, which we have been calling the inclined axis, and the h-axis are all collinear. Okay? That doesn't mean they're the same, because z is positive upwards, and h and y are positive down. There's that one difference. For the force magnitude, again, maybe you should take up golf, but for the force magnitude, we need to know the pressure at the center of area, which means we need to know where the center of area is, and just multiply that by the area. So, pressure at the center of area is either the specific weight times the depth of submergence of the center of area along the h-axis, or it's the depth of submergence along the y-axis, which again, just in this problem, because it's a vertical gate, y and h are the same. They're both vertical. So h bar, which is y bar in this case, is 4 meters plus the height, 2 meters over 2, and that gives you 5 meters. And that's what we did when we were looking at the sketch before. We all said it's got to be 5 meters. So now we can calculate the pressure at the center of area. That would be the specific weight of water, 9,800 newton per meter cubed, that's in the back of your book, times the depth of submergence, H bar, to the center of area, 5 meters, and that gives you 49,000 meters. And again, that just gives us PG. What we have to do is then multiply that by the area, and then we have the force. So when we do that, pressure at the center of area times the area gives us a force of 98,000 newtons, and it's acting on a horizontal plane because the gate is vertical, the pressure distribution on the gate is everywhere normal to the gate, and so the force acts in the same direction as this pressure distribution, normal to the gate, normal to the surface. Questions? Then let's keep going. So, we have the magnitude of the force. Now we need to know where it acts. So, let the x-axis again be along the free surface. That's 4 meters above the top of the gate. And the y-axis is going to start at the free surface, and it goes vertically downward, and we're going to have it go through the center of area. And there's a reason you know why we're putting it through the center of area. We just talked about it with the lateral location of the center of the force. So, to find the location, we always have to get YCP and XCP. X and YCP are the coordinates of where the resultant force acts. For YCP, as we just derived, that's equal to Y bar, which is the distance from the free surface along the y-axis, which here is vertical, to the center of area, plus moment of inertia about the centroid of this rectangle divided by Y bar times the area. So, you go to the back of the book, and you see that for a rectangle, the moment of inertia about the center area, that should be IG, and I corrected that, but I don't know if I corrected the corrections, is 1/12 pH cubed. And what I reminded you last class, be painfully aware of what they call B and H in these formulas. Sometimes it's going to be turned 90 degrees from what's in the back of the book, and you have to know that. So in this formula, B is 1 meter. That's the width of the gate into and out of the board or into and out of the paper. The height is the 2-meter height of the gate. It's along the h-axis. So we can calculate the moment of inertia to be 0.667 meters to the fourth. And now we can substitute that into the equation on the top of the slide. We've already calculated that Y bar is 5 meters. And so we would add that to moment of inertia over Y bar A, and we would get that YCP is 5.067 meters. So remember, Y bar is 5 meters, and YCP is 5.067 meters. It's just below the center of area. But it is below. So this is what we just found. Here we go. So ignore the left-hand side on the X first. What we just found is Y bar is 5 meters, and YCP is 5.067 meters. If we're now looking at the lateral location of where CP resides, if we put the y-axis, as we said early on, we're going to put that right through the center of area. When you do that, you ask yourself the question, is that an axis of symmetry? Yes, it is. For a rectangle, it's an axis of symmetry. And since this y-axis is an axis of power, since it's an axis of symmetry, this is 0, and xp is x bar, or all that says is that the center of pressure is acting directly below the center of area. So x bar, y bar is the location of the center of area. So x bar would be half a meter across from either side, since it's 1 meter width. Y bar, or the location of the center of area G, is 1 meter down from the top and 1 meter up from the bottom. So in this case, when we say this, it's basically saying that this center of pressure has the same x dimension as G, or that center of pressure is directly below center of area on the y-axis. Got it? Right. So, summary. We calculated the resultant force. That's one thing we were asked to do. The next thing we were asked to do is to calculate where it acts. We know it acts 5.067 meters down from the water surface, or 1.067 meters down from the top of the gate, because the top of the gate is 4 meters below the surface. So this was the system we were looking at, right? What holds that gate in place? What's holding the gate in place? Just put it in the water and it just stays there, right? So in this case, in this example, you have these rails that the gate is sliding up and down between. And so the rails are providing a counterbalancing force. That's what holds the gate in place. So if you were doing a structural analysis, here's the gate one. You're looking at the edge of it. You just calculated the force of the water on the gate on one side. And what's counterbalancing that but the rail force, the left rail and the right rail, left shark, right shark. So they're each giving you a force. And you could certainly do a force equilibrium and a moment equilibrium and calculate exactly what each one of those were. If this is a nice rectangular symmetrical object, RL and RR are going to be the same, right? So again, this is the reason why we're calculating the forces, so we can do other portions of the design. This is the load, basically, we're calculating. So let's make it a little more complex. Again, walk and then run away screaming. So if the gate, instead of being held in place by the rails, but rather just a hinge at the bottom, and I'll draw a picture of this, what would be the necessary moment at the bottom applied at the hinge to hold this closed? So think of a mousetrap, right? You take that metal rail and there's a spring. That's what the hinge is. There's a spring there. And if you're holding the mousetrap open, you're applying a force at the top of basically the gate to counteract the moment that's being created at the spring. If you don't apply that force, you have mouse fritters for dinner. Right? So here you have the gate. You're looking at the edge of the gate. And instead of having rails on either side to hold it in place, this force times the moment arm, L, is creating a moment about the hinge. And if you don't counteract it with some restoring moment, then the gate just opens. Okay, and so instead of a force equilibrium, we're looking at a moment equilibrium in this case. And so what we would say is, if we take the sum of the moments about the hinge, and what this means is any moment acting in the clockwise direction, the universal positive, is a positive moment. So if you think of F, it would create a rotation if the gate were opening in a clockwise motion. So FL is a clockwise moment, and it would be counteracted by a counterclockwise moment at the bottom in order for this system to be just at equilibrium, in order for the gate to stay closed. If you don't apply M, the gate opens. And that hinge can be at the top, it can be on the sides, but all these problems are solved the same way. You're either using a force equilibrium or a moment equilibrium. So again, L is the moment arm for the force. So this is our free body diagram. Whenever you get one of these problems, it's probably best to do this first. So it's the same problem. We had 4 meters of depth of submergence above the top of the gate. The gate itself is 2 meters high, and the depth of submergence to the center of pressure was 5.067 meters. And so if the bottom of the gate is at 6 meters below the free surface, then this moment arm is the 6 meters minus the 5.067 meters, or 0.13 meters. That's L. So we just calculated L. Earlier we calculated F. So now we just calculate the moment. So some of the moments about the hinge, again, clockwise positive, FL minus hinge would equal to 0, or if we bring the moment about the hinge to the left-hand side, it would just say that the moment is equal to FL, and F we calculated to be 98,000 newtons. The moment arm we said was 0.93 meters, and so that means the moment base will be 91,100 meters.
We have a question about what L is.
Okay, L is the moment arm of the force about the pin connection on the bottom. And so if we're asking the question which has been posed here, what is the moment at the base to hold the gate in place? Nothing else is holding this gate in place. Just like the spring on the mousetrap. The only thing holding this gate in place is the moment being placed at the base. So in order to calculate that moment, again, what we're looking at is a moment equilibrium. Some of the moments about the hinge. And the moment about the hinge due to the force is the force times its moment arm L. L is always a distance measured perpendicular from the line of action of the force you're looking at to the point in question. So, we can work problems in a static equilibrium. When I talked about the rails, we said that the force of 98,000 newtons was being offset by a left rail force and a right rail force. And if you had an equal distribution of the forces, RL and R would be the same. That's a force equilibrium. Sum of forces equals 0 in any direction. Or, again, this is a static equilibrium case. You can also do a moment equilibrium. Quite honestly, you may think it's challenging to calculate the moment arms, but the reality is, when you take moment equilibriums, those can actually be easier solutions. And we'll explain why. Here's the last example. Never forget, when you have a hinge and a connection, there are also forces acting at that hinge. So if you just did a force balance and you ignored that, you're applying a moment at that pin connection. But without Fx, the whole system can move horizontally. So the gate's not swinging open, but the whole system's moving this way, right? Why? Because you didn't apply Fx, a restoring force. And Fx and Fy are forces that are applied at the hinge. Okay, second quiz for today. It's lunchtime, so I know you're hungry. Chat room versus in the class. What's the moment arm for Fx? What's the distance? Are you answering me by doing that? It is 0, yes. If the forces act through the point of rotation where you're doing analysis, the moment arm is 0. Fy is a vertical force. The gate may have a weight in some problems. That probably also acts through, if you have a vertical gate. If it's a vertical gate, it's going to act through the pin. If it's not a vertical gate, nope, now you have a moment arm, don't you? Okay, so again, sometimes doing the moment equilibrium, you get rid of those 3 moments, weight, Fx, and Fy, because they're all acting through the point of rotation. So, you can be asked questions that specifically ask for one thing. For example, what's the restoring moment to hold the gate open? That's what was the last one. Always look for, however, the open-ended questions. What are the reactions here? And when you're asked that, that means you have to get not only the moment, but Fx and Fy. Understand? And how you would do that is doing both force equilibrium and moment equilibrium. You have to do them all. So don't forget those forces. I have a half a minute left, and what I'm going to do is just continue this example next time. Actually, I'm going to do a completely different example next time, okay? So that's it. Any questions? Chat or in IRL? Yeah. Enjoy your lunch. Eat safely. See you Friday.
The chat is wondering if they won the money. I would say yes.
Answer that and say, I always favor the chat people more. But you will always lose.